Behind me is an equation that almost looks like a quadratic, but it's not a quadratic. I mean, what is this? So in this video, we will be solving this equation. However, I should probably first clarify what this is. So this over here, this is read the floor of x. And what this means is, given any real number x, the floor of x is the greatest integer not exceeding x. So for example, if I gave you floor of 2.4, this would be 2 because 2 is the greatest integer not exceeding 2.4. Something like the floor of 3 would be 3 because again, 3 is the greatest integer not exceeding 3. And we can give like a bunch of other examples. And as I list these examples, I want you to notice a pattern. On the non-negative side of the number line, it seems like the floor of the number is just the integer part of the number. It's kind of like we're chopping off the fractional part. And indeed, that is true for the non-negative reals. If we're going to go to the negative reals, such as floor of negative 1.4, then this over here would actually be negative 2, because negative 2 is the greatest integer not exceeding negative 1.4. I know it doesn't have that intuitive consistency, but it is mathematically consistent, and we have to choose that. So now that we know this, we might be shaking a little bit. How are we supposed to deal with this in our equation? Thankfully, there is a really good method for this. Observe that any x, any real number x, can be written as its integer part, so the floor of x, and then plus its fractional part. I'll denote that like this. Now, notice that the fractional part of x, by convention, should always be within this interval, right? It should always be it should always be greater or equal to 0 and less than 1, strictly less than 1. Now, this makes sense. If it's 0, then it's an integer. If it's anything in between, then it's, well, not an integer. It's like a decimal. Okay, so let's replace x with floor of x plus fractional part of x into this equation. So here we would have floor of x plus fractional part of x all squared minus 8 floor of x plus 6 is equal to 0. And now we can expand the brackets here. Here we would have floor of x squared plus 2 floor of x fractional part of x plus fractional part of x squared minus 8 floor of x plus 6 is equal to 0. And notice we actually have a quadratic expression in terms of fractional part of x if we treat the floor of x as constants. So I'm going to rearrange a little bit. And this over here is really useful because we can solve for the fractional part of x in terms of floor of x. Check this out. By the quadratic formula, the fractional part of x is equal to negative 2 floor of x plus or minus square root of 4 floor of x squared minus 4 times the constant term. So we have minus 4 floor of x squared plus 32 floor of x and then minus 24. All under the square root. And of course divided by 2. Now this over here, it's, well, conveniently going to just cancel out each other, right? And all we're left with is 32 floor of x minus 24 under the square root. Of course, we could simplify this a little bit more. The square root of 32 floor of x minus 24, this over here would be equal to, just extract a 4, so that's 2 times 8 floor of x minus 6. So altogether, the fractional part of x would be equal to, again, we can simplify, just divide top and bottom by 2. Now, over here, this is a very simplified version. Now, the fractional part of x must be a real number, obviously. So what's under the square root must be non-negative. So we can set up an inequality. We would get 8 floor of x, so 8 floor of x, and then minus 6 must be greater or equal to 0. We can solve the inequality to get floor of x is greater or equal to 3 over 4. Now, This means that floor of x is obviously positive. However, the negative of a positive is negative, and then you subtract the square root of something. Obviously negative then. So that's going to be negative if we take the negative root, right? However, we saw earlier that the fractional part of x is always in between 0 and 1. Includes 0, but not 1. So for any chance of that to happen, we must take the positive root, not the negative one. And this is officially the fractional part of x in terms of floor of x. Now, this is actually really useful because remember, the fractional part of x has a huge restriction. It must be within that range from 0 to 1, including 0, but not 1. So we can write this with an inequality. We have 0 is smaller or equal to this, right? So negative floor of x, and then plus the square root of 8 floor of x minus 6. And then this over here must also be strictly smaller than 1. And we have an inequality. Now this inequality is very useful because remember, floor of x is an integer. And if we can solve this inequality for floor of x, then we get all possible values of floor of x, right? It's an integer. There are only so many values. So hence we can get the solutions to this equation. Now to solve for this, we're actually going to consider breaking this up into two portions. We're first only going to consider the portion where it's 0 is smaller or equal to this expression. So here we can move negative floor of x onto the other side. So we get square root of 8 floor of x minus 6 is greater or equal to floor of x. And both sides are non-negative, so square both sides. So we have 8 floor of x minus 6 is greater or equal to floor of x squared. And we can move everything on this side onto this side. So we have floor of x squared minus 8 floor of x plus 6. This is going to be smaller or equal to 0. Now, this is a quadratic expression in terms of floor of x. Now, we're going to get the roots of this quadratic expression. And it might not make any sense to, solve the inequality by getting the roots, but it will in a second. I'll explain. First, let's get the roots. By quadratic formula, the roots would be 8 plus or minus square root of 40 divided by 2, okay? And we can simplify this even further by simplifying 2, 4 plus or minus root 10. Now, why did we get the roots? Well, picture an arbitrary quadratic, or even the quadratic that we have here. We know the roots, we found them, so it's these two values. So we can plot them on the graph. And we know they're on the x-axis because obviously they're the roots. They make the value of the function 0. So those are the roots, and it also faces upward, right? Leading coefficient is positive, so our problem might look something like this. Now take a look at our graph. Notice that whenever x is within the interval between the two roots, we see that the quadratic y value has a negative value, right? It's below the x-axis. Otherwise, it's above. So this tells us that whenever x is basically in between the interval of the two roots that we have here, then we see that the inequality is satisfied. It's smaller or equal to 0. So therefore, our inequality would actually be 4 minus root of 10 is smaller or equal to floor of x. And then this is smaller or equal to 4 plus root 10. And that's one inequality we have. We need to solve the other part. This part. This is smaller than 1. To solve this part, we move negative floor of x onto the other side as again. So we get square root of 8 times the floor of x minus 6 is smaller than 1 plus the floor of x. And again, square both sides because both sides are non-negative. So we have 8 floor of x minus 6 is smaller than 1 plus floor of x squared plus 2 floor of x. And we can move every term on this side onto this side. So we have floor of x squared and then minus 6 floor of x and then plus 7. This shall be greater than 0. Now over here, again, same tactic. We get the roots. So the roots over here, by quadratic formula, this would be equal to 6 plus or minus root of 36 minus 28 divided by 2. And we can simplify this to be 3 plus or minus root of 2. Now, this over here is different from the last inequality. Here, we must have this to be greater than 0. Again, examining our parabola structure, we see that for this to happen, it must be towards the right side of the larger root, right? Or towards the left side of the smaller root. Now we know what the larger root is. It's 3 plus root 2, and the smaller root is 3 minus root 2. So we have another inequality. Here we have, I'll use red. Here we have the floor of x. The floor of x must be either greater than 3 plus root 2, or we have floor of x to be smaller than 3 minus root 2. And one important note, okay, very important. This is a strict inequality. We don't have the possibility for an equal expression. So that's why I wrote strict inequalities instead of, greater or equal to or smaller or equal to. So please be careful when you're solving inequalities like this. Notice the notation. Okay, so we have two separate inequalities. I put brackets around them to separate them. And we're going to find their intersection, because according to this inequality, both of these have to be true. Now, I've drawn a number line and labeled the relevant points, so we're ready to graph. We're going to graph it like this. First, consider this inequality. We know that floor of x is within the interval from here to here, right? So we're just going to draw a big arc connecting them. Now, over here, we have this big region, but not all of the integers in this region might be valid. We have to consider this next one. Floor of x is greater than 3 plus root of 2. Well, if that's the case, then we must have from here, and it just spans outwards, going on forever. And one more note, this cannot be accepted, so we draw an open circle here. So this specific point cannot be accepted, but everything else is good to go. And for floor of x to be smaller than 3 minus root 2, well, that would be this, right? It goes on in this direction, and this point itself cannot be accepted. And now we see the intersecting regions. We have this as an intersecting region, right? And this as an intersecting region. All that's left is to find all of the integer points, because floor of x can only be an integer. So what can floor of x be equal to? Well, according to our inequalities, floor of x can either be equal to 1, so that's representing 1. Okay, well, none of these satisfy, so we go to this one. Aha, this one does satisfy. So this one is 5, this one is 6, and this one is 7, and this one is 8, but that does not count. So here we have all the possible values of floor of x. Now that we have all possible values for floor of x, we just need to substitute them back into the equation, and we can solve for x. First, let's rearrange a little bit. We have x squared is equal to 8 floor of x minus 6. And when we have x is equal to 1, we would have 8 minus 6. Sorry, when we have floor of x is equal to 1, we have 8 minus 6. So that'd be x squared is equal to 2. And our solution for this one is x is equal to root 2 only. Now, the reason it's only positive root 2 is because if we did negative root 2, then the floor of x would no longer be 1. But the floor of x is 1. So you have to have them both matching. So it's only root 2. Now, for floor of x is equal to 5, we would have 40 minus 6. That would be x squared is equal to 34. So we have x is equal to root of 34. Again, only positive for the same reason. When floor of x is equal to 6, then we have x squared is equal to 42. And again, x is only equal to positive root of 42. And when floor of x is equal to 7, then we have x squared is equal to 50. So x is equal to, again, only positive 50. And of course, you could also simplify this as 5 root 2. Or if you want to just make it consistent with, an integer under the radical, then just write root 50. Well, that concludes it. We have all our solutions. I'll write them down here because this looks kind of clumped up. So we have root 2, we have root 34, we have root 42, and root 50. And those are our solutions. And in case you're wondering, yes, each of these numbers is consistent with what their floor values are. You can check for yourself. Anyway, we have our solutions. I hope you found this video interesting. If you did, please do consider dropping a like and subscribing. Thank you very much. Bye.